In this video, I am going to review the steps for a hypothesis test for one proportion and then go through a couple of examples. So remember that a hypothesis test is used to test whether the difference between the assumed value of a parameter and your sample statistic is likely the result of random sampling error or unlikely the result of random sampling error. When the difference between your sample statistic and assumed parameter is found to be unlikely, then we say that that difference is statistically significant. So this is a very important term here, statistically significant. When you take data, you will always have slightly different values based on random sampling error. But some deviation from the true value is more likely to occur than others. And when you get a difference that is too large to be considered likely due to random sampling error, that's when the difference is statistically significant. So not every difference is statistically significant, and you often can't tell just by looking at the numbers. You have to do the test. We define unlikely by assigning it a probability called the significance level, denoted as alpha. And we're going to use alpha 0.025 for our one-tailed tests. The assumption that the parameter is equal to a certain value is the null hypothesis, denoted as H sub 0, H naught, H0, HO. And so this is always a statement of equality. This is the assumption under which we do the test. And if the null hypothesis is rejected by finding a difference between the assumed value and the sample value to be statistically significant, the alternative hypothesis is supported, right? So statistical significance occurs when the difference is too large to have occurred by random sampling error or too large to have likely occurred by random sampling error, in which case we reject the null hypothesis and support the alternative hypothesis. The alternative hypothesis can either be that the population parameter is less than an assumed value, greater than an assumed value, or not equal to an assumed value. I prefer to work with assumptions of less than or greater than rather than equal to. So the steps. First thing you need to do is state your claim. And this will usually be a less than or a greater than. Once we have our claim, then we know the value we'll be working with, and we can formulate the null hypothesis that our parameter is equal to that value. And we can formulate the alternative hypothesis, which is the parameter is either less than, greater than, or in some cases not equal to the assumed value. If we're working with the less than, it's a left-tailed test. If we're working with a greater than, it's a right-tailed test. If we happen to be working with a not equals to, it's a two-tailed test. We choose our significance level alpha, which defines our unlikely, and it's the complement of the confidence level. If the confidence level is 95%, the significance level is 5%, but we are going to divide that 5% equally into the two tails to test our one-tailed, either left or right-tailed tests. So we use an alpha 0.025, but you could have something less than that. We then compute our sample statistic if we have not yet done so, the standard error, and any other statistics that are necessary. And then we compute the probability value. And this is the probability of actually obtaining a value as extreme as the one we computed from our data. So it is the area in the tail as defined by our test statistic computed from our data or sample statistic. If the test is left-tailed, then the p-value is the area in the left tail as defined by our sample statistic or test statistic, depending on what we're using. And if the test is right-tailed, the p-value is the area in the right tail as defined by our sample statistic. If it's two-tailed, then we find the area in the tail defined by that statistic and then double it. The decision rule. This is where we decide if we're going to reject the null hypothesis or fail to reject the null hypothesis. And to do that, we compare our p-value to alpha. If our p-value is less than alpha, then we find that the probability of obtaining a value as different from our assumed value is unlikely to have occurred under our assumption. So we reject our assumption, which means we reject the null hypothesis. Since we reject the null hypothesis, we support the alternative hypothesis. Now, if the p-value is greater than alpha, that means it was likely to occur under the assumption, so we do not reject the null hypothesis. It's not as strong a support for the null hypothesis as rejecting the null is in a support for the alternative. So your conclusion to support H1, if it's your the conclusion to support H1 is a stronger conclusion than supporting H0. And once we have our conclusion, we write the sentence, the sample day supports the claim, or the sample data did not support the claim based on whatever the decision rule was. So let's look at the example we looked at before, but now we're going to just write out the steps. So we have 785 randomly selected subjects who completed 4 years of college, and 144 of them are smokers. And we want to test the claim that less than 20% of college graduates are smokers. So we start off with our claim that P is less than 0.2. Now we can form our null hypothesis, which is always a statement of equality. So this is the statement P equals 0.2. And remember, this is what we use as our assumption when we talk about finding our p-value. The alternative hypothesis is our claim, and alpha is 0.025. So this is our setup, these 4 parts: the claim, the null, the alternative, and alpha. Then we can get to our computations. And for a claim about a proportion with one data set, we need to find p hat. And so p hat here for the smokers is 144 divided by 785. So p hat is 0.1834. We can compute our standard error, assuming that the true population proportion is 0.2. So we get the square root of p, which is 0.2, times 1 minus p, or 1 minus 0.2, divided by, don't forget the close parentheses, divided by the sample size, 785. Once we know p hat and SE, we are ready to compute our p-value, which is the probability of being in the tail as defined by the 0.18. So let me go ahead and draw another picture or that you can see. So here's our null. This is our sampling distribution. Our null is here, that p equals 0.2. And then here is where we had our p hat. Anyways, here's where we have the p hat is equal to 0.18. So the 0.18 defines this left tail, and the area of that left tail is what we call our p-value. All right, so let's compute that p-value. We're working with a normal distribution, and we want to find the area less than 0.18. So with Excel, that means we are going to use the norm.dist. Don't forget to write equals first. Norm.dist. So the first input is this 0.18. So what's represented by X here is the score on the horizontal axis that's defining our tail, and that's the sample proportion. So 0.18, or it's just better to click on what we've already computed, comma. The mean is our assumption from the null hypothesis, so that's 0.2, comma. Standard deviation is the standard error, so I'll click on that. And when we are finding probabilities, cumulative is always true for norm dist. So we get a p-value of 0.123. So when we look at our decision rule, we see that the p-value is greater than alpha, which means we fail to reject the null hypothesis. And so our conclusion is the sample data do not support the claim. All right, so that then is a full hypothesis test that you would write up for your homework assignment. Let's do another example using the same data, but with a different claim. So same example, same data, different claim. So let's start over here. I am going to delete all this, and we are going to do another one with a different claim. So what I'm going to claim this time is that our sample proportion is less than 22%. So claim P is less than 0.22. Null H0. P equals 0.22. Alternative H1. P less than 0.22. Alpha is 0.025. Now we do our computations. Start with P hat. This hasn't changed from our last problem, so it's still the 144 divided by 785, so we still have the 18%. But now the standard error will be different because we have a different value for P. So this time we are assuming that P is 0.22. So we have 0.22 times 1 minus 0.22, close parenthesis, divided by 785, close parenthesis. So our p-value will be different. So the p-value is norm.dist p hat, comma, the 0.22, comma, the standard error, comma, true. And notice now how much smaller this p-value is to the one we got previously, right? Previously, we had a p-value that was bigger than alpha, but now changing the claim from 20% to less than 22%, we end up with the p-value that is much smaller than alpha. So this time, the decision, we have P value is less than alpha, so we reject the null hypothesis and support the alternative. The alternative, remember, is our claim right here. Claim, alternative. So if we support the alternative, we support the claim. So our conclusion is the sample data support the claim. So it doesn't take too long to do one of these when you understand what you're doing. Let me go ahead though and draw just a picture so you can see what's going on like I've done before. Sampling distribution of the proportion is normal with the mean equal to the assumed parameter. So that would be P equals 0.22. We got a p hat of 0.18, which we know is less than 0.22. So that value down here. So here's our 0.18. And that is our p hat. And so the p-value will be this area here in the tail, and that p-value was this time small. So this time we had a small p-value. So I really could have drawn this a little differently. I could have, since it was so small, without doing the labeling, let me just show you more what it looked like. So it would be like way down here and you get this little tiny area. It's really more what it looked like, something like that. All right, well, thanks for watching. Be sure to look at part 3 for a claim that contains a greater than alternative hypothesis.